All right, so here we are. We're going to talk about capacitors, introducing a new component. Basically, up to this point in the class, we have only learned about voltage sources, current sources. Those are our types of sources. We had some dependent sources that we saw. And then as far as passive components, components that just behave a certain way, have some current voltage relationship in our circuit in response to some source or some input. We've only talked about resistors, and so now we're introducing a new type of component called a capacitor, and then later we're going to talk about inductors later on in this module. But these components definitely make the circuit analysis a little bit more complicated. They behave much differently than resistors do, and so we need to make sure that we understand them, and we are going to just move into what is a capacitor right now. I'm going to talk about the capacitor. This right here, this picture on the right hand side is a picture of what a capacitor might look like. Of course, you're not going to see the electric field lines in real life, but it is by definition two conductors separated by some distance, or typically that distance is occupied by an insulator or by a dielectric. The dielectric is just an insulator that basically is good at storing an electric field, or good at polarizing when an electric field is applied across it. Okay, so by definition, that's what a capacitor is. Anytime you have two conductors, so this plate might be a conductor and this plate would be some other conductor, so maybe they're both made out of copper. And then even if the middle part, this distance here, was just air, that, air is an insulator. It's not a great dielectric, but it is an insulator. And so that would be a capacitor, okay? Different materials give better dielectric properties, and so they're used to make better capacitors with higher capacitance. The second point here is that capacitors store energy. Okay, so up to this point we learned about resistors, which don't store energy, they dissipate energy. Okay, we haven't really gotten into that much. I haven't talked about power dissipation or energy dissipation, but resistors dissipate energy, and they do not store energy. An ideal capacitor does not dissipate any energy. It actually only stores energy, okay, in the form of an electric field. Okay, so let me highlight that. It's important to note this is not something that you're going to probably be tested on, this particular fact that capacitors store energy in the form of electric fields. It's just important to note that they store their energy differently than the way that inductors store their energy, which we'll talk about later on when we get to inductors. Okay, so the first point here, that a capacitor is two conductors separated by an insulator. The second point is that they store their energy in the form of an electric field, which we can see the E field here. And third point here is that capacitors behave like an open circuit for DC, okay? So let me move this out of the way. If I draw a DC circuit here with a voltage source, let's say this is a 9-volt source, and then I put a capacitor right here in series. In my circuit, okay, I would have 9 volts right here, I'd have 0 volts right here, and so the voltage across my capacitor would be 9 volts. And so if this was a resistor, we know that we could use Ohm's law to determine the current flowing in the circuit. However, the IV relationship of a capacitor is not the same as the IV relationship of a resistor. Instead, which we'll talk about a couple slides from now, capacitors behave like an open circuit for DC. So there's actually no current flowing in this circuit, even with a voltage across my capacitor. Okay, so that's an important concept. And so I'll go ahead and leave this video here, little introduction to the capacitor, and then in the next video, I'll talk about capacitance and what kinds of things, what kinds of properties of the capacitor determine how much energy and how much charge it can store.